Hello and welcome to another video. In this video we're going to be doing cherry pickup 2, and in the problem you're given a rows by columns matrix grid representing a field of cherries where a cell represents the number of cherries that you can collect from it. And you have two robots that can collect cherries. Robot 1 is located up here, robot 2 is located over here, and return the maximum number of cherries using both robots in the following rule sets. Robots can move either down to the right, or down to the left. When any robot passes a cell, it picks up all of its cherries and it becomes empty. When both robots are in the same cell, only one of them takes them. Both robots cannot move outside of the grid at any moment. Both robots reach the bottom row in the grid. So essentially, this is basically like a DP problem with a few constraints. It's actually not that hard. Like, there's a lot of stuff here, but if you break it down, it's not that hard. So let's kind of walk through what happens. So here's example 1, and they show you the optimal path for the robots. So here, this is like this, which is 5 plus 5 plus 2, which is 12. And here, this is the other path, which is also 12. So here you would get 24 cherries. Then in the second example, they have the paths again. So the path for the left robot is 10, 17. And then the path for the right robot is 11. So total 28. But essentially, if you think about it, like the cells, the rows and columns are only 70, right? So you can have like a decent amount of dimensions here and it would be fine. But essentially, let's just kind of like figure out what we would need to have, right? For this kind of problem, for this to work. So if you think about it, whenever we are on a row, we need to know where both robots are. So, right? So let's say we're on this row. We need to know like where both robots are. And what are all the dimensions the robot can be? Well, it can only be in one of the columns, right? So whenever we're on a row, a robot can only be in one of the columns. And then wherever they are, like let's say we're here and here, where they can go is also kind of obvious, right? You can just take one robot's location, try like here, 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 and take the other robot's location, try here, 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 and get all those combinations. So one combination would be like the left robot goes left, the bottom robot goes left, then you can have like the left robot goes left, the bottom robot goes down, left robot goes left, bottom robot goes right, and so on. So every one of them can make 3 moves. So in total, you only have to check 9 places. And it's very easy to check out of bounds as well. You can just say like, oh, you can handle it in whatever you want, but you can just check like what's my robot's index and where can it go. But essentially, you have some state, right? One robot's column, the second robot's column, the row, and then you recurse to 9 different states, right? So like I said, one state would be like, let's say you aren't checking for out of bounds, you would recurse over here and over here. Another one would be like over here and over here. Another one's over here and over here. And then like so on, over here and over here, over here and, or sorry, over here and over here, over here and over here, and over here and over here. And the last one is here, 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 and here, here, right? So those are pretty easy to do. Then when you recurse, if we have the location of both robots, it's very easy. Like what are our cases? Well, if the robots are on the same cell, then you only count that number of cherries once. If the robots are in different cells, then you add both of those together and you recurse down. And what's your, like, when are you done? When you traverse through the grid. So whenever you're over here, when your robots are on this row over here, that's out of bounds, right? So that's pretty easy. So we can write this down in like a DP thing. So for state, we can write down bot 1 column, bot 2 column, and row, right? So that's what we need to know. That will tell us our entire state, right? They're always going to be on the same row, and they're going to be on some column. Then what about our base case? So our base case is when we are at the end of the grid. And by that, that's going to be pretty easy to tell because, like, let's say we have our row numbers. Let's say this is like 0, 1, 2, 3, 4. If we have 4 rows, then or here we have 5 rows. If we're on row whatever we have, like if we have 5, if we're on row number 5, that means we're done. So how many cherries can we return when we're at the end of the grid? This should just be 0, right? Now, you can do this one of 2 ways. So the way I'm going to do it is when I recurse, I will check for invalid cells. So I will recurse, like, let's say in this robot, like I recurse with this robot going right and this robot going right. I'm going to recurse here, and then I'm going to check, are both my cells valid? So I'm going to have another base case here, robot out of bounds. Now you could do this before recursing. Either way is fine. So in my case, I want this to never be like a valid state. I never want this to give you the maximum amount of cherries. So in this case, I will just return -infinity. And that will ensure that this state will never be like the best if I'm trying to maximize. And finally, recursion. Take cherries for both. If they are on same cell, don't count cherries twice. Right? So they said that if two robots are on the same cell, you only count the cherries once. If they're both like over here, let's say, I'm only going to count this once. But if they're on like this cell and this cell, then I'll add these together. So take cherries for both and recurse to 1 of 9 locations. Right? And 1 of 9 because each robot can move in 3 directions, either left, straight down, or left or to the right and down. And same one here, 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 here. And we'll just check all 9 of those possibilities. And then the maximum here will give us the result. And that's basically it. So let's take a look at the code for this. And I think what I decided, and you guys can let me know what I think for problems going forward, I will try to just not write the code because it just takes up like a lot of time and you don't really learn anything. You're just basically copy pasting the code. But instead, I'll just go over it in depth. So here's our DP solution. So first we get the number of rows in the columns. Then we have our 3 states, like I said, the bot1 column, bot2 column, and the row we're on. If we are out of bounds, right? So if this is 5 rows and we're out of bounds, we will just return 0 because we're out of bounds. Now this cache decorator lets us handle caching automatically, or you could have a cache as well. And finally, or not finally, but we have another base case, like I said, where if one of these bots is out of bounds, so we just check, okay, what's the minimum of the bot1 column, bot2 column? If it's negative, or the maximum of bot1 column and bot2 column is greater than or equals columns, that means we're out of bounds, so let's just return -infinity. Finally, we're going to record how many cherries we have. And if the bots are on 2 different locations, then what we want to do is we want to add both bots. But if they're on the same location, we'll just record the 1 cell. Then we just set our result. And we try every single one of 9 things. So essentially, I had it like this. So basically, let's say you're on column X. You want to go to column X minus 1, column X, and X plus 1 to the next row, right? So this will basically handle that. -1, 0, or 1. And same thing for the second bot. So we're just basically trying all 9 combinations with this nested for loop. We just take bot plus I, bot2 plus j, and the next row. And we're always going to be adding the total that we got from our current cells. So we put that in the result. We try to maximize it, return. And finally, the initial state is the first bot is on column 0. The second bot is on the last column, and they're both on row 0. So you just call this DP function with this, and let's try that and submit. And you can see it's pretty good. But as always, and this is why I think not coding is going to make this better, because then I can also explain other solutions quicker. So notice that, and we've done this in a lot of videos, notice that our recursive state is just recursing to the next row down. Same thing in our picture, right? Like we have some states for some row, like let's say this row, we have some states, but every row only relies on the row below it or the row above it, right? So like this row, the number of cherries we can pick up depends on where the robots can be in this row and how many we've picked up so far. Then for this row, the number of cherries we can pick up all the way down to here depends on how many we can pick up over here and where the robots are here. So because every row relies on only the 1 row above it, we can actually get rid of that with space optimized bottom up. And you might be able to do this with an array, but because this is a 3D DP, I actually used a dictionary for the DP for the bottom up, and let me show you here. So I'll kind of walk over it and explain everything. So here is our initial DP array, where the first, what we're going to track is the column of bot1 and the column of bot2. And bot 1 starts at column 0, bot 2 starts at column -1, and the value will be the total amount of cherries we'll have picked up when we're at this location. So the total amount of cherries we're going to pick up is going to be the first column at row 0 and the last column at row 0. And then we're going to loop through every single row. And for every single row, we're going to make a new DP array, right? So this is the standard template that I recommended for space optimized bottom-up DP. You have a dimension you're trying to get rid of, which is in our case the row. You make a new DP, and then you loop through the rest of it, the things you're not trying to get rid of. So the things we're going to loop through is going to be our previous dictionary items of our previous row. And our dictionary is going to be in the format of, like I said, the key will be bot 1 column, bot 2 column, and the value will be how many cherries we would have picked up. So through every previous value in the previous row, we're going to once again make these 9 moves. So this is very similar to memoization. That's why memoization is good to code up, because the rest of it's very similar. Like I said, you can probably code this up with an array, but because this is 2D, this is like a 3D array going down to a 2D array, I feel like a dictionary is just a little bit more intuitive. So we're going to go through all of our previous values in our previous row, make all of our moves that we can, right? So we just calculate like where these bots can go to. And then we figure out, are these actually in bounds? We actually have to handle being in bounds. We're not recursing, so we're checking for being in bounds before doing these things. Then we calculate a total. And so the total is basically the grid of the current spot we're in. And we have to check, is the location for the first bot the same as the other bot? Kind of like the same thing as literally here, right? So we get a total. If they're on a different spot, then add the other ones. This is basically the same thing. So you get the location for the first bot, and then you add the location for the second bot if the 2 locations are different. Otherwise, just add 0. Then finally, because you might get to this cell multiple times from other cells, like let's say we're calculating this cell, and on a previous cell, maybe one of our DP things is like both bots are over here. Now, one of the recurrence relations is they both go here. But also you can have another way of getting here, right? Like let's say the bots are here and here. You can also go here. So because you can get here in multiple ways, like both bots can get to the exact same location in multiple ways, I just said, okay, if we do have a value here, then let's just see what value we had before, and let's see what value we got now from our cherry. So for example, let's say we're going to this cell, and our previous state was both bots were maybe like over here. So our previous value would have been like 3 plus 1, which is 4, plus 5, which is 9. And then we come over here, they both come over here, so that's going to be 14. But what if we come over here this way? Then our previous value would have been this whole path, so 5, this whole path, 2, so 7, and then they both come over here, which will be 12. So this is going to be worse, so we're just saying, like, figure out what was here before, and then if you come here again, just only store the best value. So that's what we're doing here. So our new DP value, now because we use a default dict, if we were never here, it will just default to 0, right? Like this will basically just default to 0, in which case our current value will just always be better. But if there was a value, then store the best one. Then finally make your DP, like I said, instead of array, I just have this DP dictionary, is the new DP. And so that's basically what happens here. So we can walk through a little bit just to explain this. So let's kind of walk through our rows, and just to show this, like a few rows, because this is like kind of small. So our initial state here for row 0 would be the first robot is at column 0. The second robot is at column 2. So this is our key, right, where the robot location is. And then our value will be the total cherry, so 3 plus 1, so 4. And this is the only place they can start. Now for the next row, we can basically figure out, okay, from this location, where can they go? So one spot they can go is here. Another spot they can go, well, robot 1 can go, so I guess maybe we'll draw those in another color. So robot 1 can go here. That's one possible thing. And robot 2 can come over here. So let's do this is a possibility, right? If this one goes here and this one goes here, that's a possibility. So how many would we pick up? And like, what would the locations be? So the locations would be robot 1 would be at 0. Robot 2 would be at 1. And the total here is the previous value, right? So the previous value is 4 plus this whole thing because they're at different cells. So 4 plus 7, so we get 11. So that's one possible state. Another possible state is instead of this robot being over here, this robot can be over here instead. So these two, in which case, what are our cells and what's our number and stuff? So let's write that as well. So this is going to be row 0, and this is going to be, or column 0, and this is going to be column 2. And the total value will be the previous 4 again. This will give us 2, so we get 6, and this value over here will give us 7. So that's basically the only two ways if this first robot comes here. Now the other two things we can have is if this robot over here comes over here, and then this robot can also go over here or over here. So let's do those two ways. So let's say this robot, let's maybe draw this in a different color because I don't think I can erase. So let's say this robot comes over here and this robot comes over here. Let's do that. Let's do that one. So that's going to be, they're both going to be at the same exact index. So 1, 1, previous value, which is 4 plus 5. That's only counted once. So this is 9. And the last one is going to be, this one still comes over here, but now this one comes down here. So this is going to be, let's draw that over here, 1, 2. The value will be 6 plus the previous value, so 10. And so these are all the possible states you can have for row 1. Then for row 2, you take all these states, you figure out where they can go and so on. This is going to get like really big once you do more rows. But that's kind of the idea, and that's why I think a dictionary is easier. Maybe you can use an array, but that's kind of the idea. You store a dictionary for every row of key value pairs where the key is just a tuple of bot1 location, bot2 location. And so, yeah, so that's basically it. And we can comment this out and run this one instead. And yeah, I do think this was really nice because like if I was coding this would take like an extra 10 or 15 minutes and you wouldn't really learn anything. So I think going over stuff is a lot better than coding. But yeah, let me know what you guys think about that. So anyway, so we can code this, we can run this. And you can see it's still pretty efficient, but the space is a lot better. Like this was like 60 megabytes originally. Like if we look at submissions, yeah, this was 60 megabytes and we cut it down to 17. So yeah, because we got rid of one of our dimensions. So let's go through the time and space for this particular solution. So essentially, if you think about it, it's basically going to be like, what are the dimensions we can have? Like, what are all the different things we can have? So it's basically going to end up columns squared times rows, right? Because all the different possibilities you can have for the robots is not exactly column squared, but roughly, right? Because robot 1 has a column, robot 2 has a column, and they're on the same row, and you have to go through all the same rows. So this is going to be like c squared times rows, or rc squared or something. But now the space is only c squared, because we're only storing all the combinations for a particular row instead of storing this entire matrix. So that saves us a lot there. So yeah, hopefully this was helpful. Let me know what you guys think about this new format where I think I will, maybe for the easy problems I'll code it where it's like 5 lines of code, but especially for these, like it just cuts down the videos by like 15 minutes and I can go a lot more in depth and stuff instead of just writing stuff down. So yeah, if this was helpful, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.